Hello everybody, today I'll be your SimCFI, and in this video we're going to cover slow flight, stalls, and spins. Let's pause this real quick, do a quick little ground lesson. So, a stall happens when your airfoil, your wing, exceeds the airfoil's critical angle of attack, and that critical angle of attack will always be a fixed number, the same number, for that specific airfoil. And for most general aviation airplanes, training airplanes like the 172, that angle of attack tends to be around 17 or 18 degrees. Now, angle of attack is defined as the acute angle between the chord line and the relative wind. You could also call it the airflow. You got your plane's direction, your flow of motion going this way, and the relative wind is opposite the direction of motion. And so chord line is a line drawn from the leading edge to the trailing edge. So the chord line versus the relative wind defines your angle of attack. Now so to stall, to bring it down to that point, it's got to exceed the critical angle of attack. So if we look at this VG diagram, V for velocity, G for load factor, you'll see that maintaining level flight, which is 1G, cruising around 120 miles an hour, right here in this normal operating range. But if we just pull the power back and maintain altitude, and we just keep slowing down, or if we're just in a constant descent like 500 feet per minute for landing, wings level, power's off, and you just bring it, the speed goes down and down, you're going to get to this point where that's the normal stall speed. Wings level, 1G, this is your normal stall speed. And for this, whatever this airplane is, it's about 65 miles an hour. And so now, it changes though when you turn. When you start banking the airplane will increase the load factor. And that is seen in this chart here. So you bank angle in degrees versus load factor and percent increase in stall speed. So 20 degrees of bank, 20 to 30 is what I say to use in the pattern roughly. And you can see that doesn't necessarily increase your stall speed all too much. You have a 8% increase of stall speed, and you're barely doing 1 point some G's. Now, if you want to do 60 degrees of bank, now given if you're descending to land, you're not going to be level flight, but if you're 60 degrees of bank, maintaining altitude, you will be pulling 2 G's, and this is true for every airplane. And so this is why we do lower bank angle as well in the pattern, especially slower speed. So at 60 degrees of bank with 2 G's, that's going to increase your stall speed by 40%. So you take whatever your normal stall speed is and multiply it by 40%, and that's your new stall speed at that bank angle, given that you're holding altitude at 2 G's. So this chart is useful. You can see how that works. Now in a Cessna 172, you're not really going to maintain 90 degrees of bank and maintain altitude. You're either just going to stall out or just going to descend. You're not going to maintain. So you're not going to get, infinity G's. So there's practical limits to the chart. So looking back at this now, that 60 degrees of bank gives us 2 G's. And so if we're going around 120 miles an hour and we bank 60 and hold that and we hold 2 G's, we'll be right around here. But now if you slow it down, you're in the pattern, and you bank at 60 degrees going 85, 90 miles an hour, maybe in a little faster airplane, 2 G's is going to stall. So this line is where it's going to have an accelerated stall. Accelerated stall is basically when you're stalling faster than your normal stalling speed. And you can see up this chart, all these areas up here, this is structural damage and structural failure in the yellow and red. So this is where your maneuvering speed is established. And maneuvering speed is where you could bring it to that accelerated stall point and just stall the airplane if you're below maneuvering speed and be safe. If you're going faster than maneuvering speed, like 140 miles an hour, and you end up pulling 5 G's, then you can potentially cause structural damage. And if you manage to get up to faster, 180 miles an hour, and pull even more G's, you can do structural failure way up here. And so this maximum structural cruising speed is the beginning of the yellow arc right here. And so that's why in turbulent air, you want to, if it's not too turbulent, you want to be at or below the yellow arc. You want to stay in the normal operating range. And if it's really turbulent, you want to stay below maneuvering speed, because if you're over here at 160 miles an hour and you encounter enough turbulence, you'll have not random, but you have momentary spikes in load factor, and you don't want it to spike up into the structural damage area. You want it to spike up through a stall, so you stall before you damage the airplane. And then this is the yellow arc to red line, the caution range. And so you can see that you're at a greater risk of, you had a faster speed, you got a greater risk of getting into the structural damage area. And then this is your VNE, the red line, the never exceed speed. And usually the VNE speed is determined by control flutter. If you start going faster than VNE, you might lose control. But also, if you put any load factor on the airplane, you could start having structural failure almost immediately. Alright, so that should be enough to get you the concepts for what's happening when the airplane stalls. So let's get in the airplane here and get going. So right now we're at 3,000 feet. There's the Sutter Buttes. Yuba County Airport's way back there. We've been flying west for a little bit. So now let's set up slow flight. To do slow flight, I'll move this yoke so you can see the tack for now. Slow flight, according to the PTS, you're going to be in your landing configuration, and you're going to slow down to a speed to where if you slow down any more, or if you if you change your pitch or your speed at all, then you bring on a stall. And so essentially we need to get down right to the bottom of the white arc here. And then for private pilot you get that speed plus 10 knots, and for a commercial pilot you get that speed plus 5 knots, and it's minus 0. And that should be because if you go down speed at all, then you stall. So let's maintain 3,000. We'll pull back the RPM to 1,500 RPM. Oh, and you gotta maintain your heading plus or minus 10 degrees and your altitude plus or minus 100 feet. So 1,500 RPM roughly gets you into the white arc. We can start adding flaps. And since we're already below 85 knots for the top of the white arc, we'll just go straight to full flaps now. Maintain coordinated flight. And now we can trim a bit. You don't want to trim too much, because if you have to get out of it and you apply power, the airplane's just going to pitch up really fast like that if you apply power with a lot of trim. So now we're coming up on our speed here. The stall horn's going to yell at us. We're losing altitude, so we got to add power. This is also where the pitch controls the airspeed and power controls altitude concept comes into play. And I see I'm going to have to hold more and more right rudder as we get into this. So, right around 40 knots is, for a private pilot, that's the middle of your tolerance, your plus 10 knots. Alright, so we're going to maintain heading here. And now, if we see how we're slowly descending, we're at 1,900 RPM. And so now I'm going to have to add power to climb. And that's a little bit of a stall. At full power. Let's control that a bit. We'll try to keep it around 40 knots for the sake of the demonstration for slow flight. So we're pitched again. You wanna keep your pitch angle relatively constant and add or remove power to climb or descend. So right now we're at 40 knots, that's good. Let's go ahead and climb. And I'm full throttle right now. Okay, we're 3,000. I'll reduce the throttle a bit. And then control the airspeed with pitch. So this is slow flight. So now, in the exam, in the check rate, they could ask you to turn. So let's turn left to 210. You're going to want to use no more than 10 degrees of bank. And it doesn't take very much. Okay, we've climbed up too high. You need to reduce power. It's already 150 feet over target. Getting a little bit too slow here. Okay, so here's 210 heading. Not doing the best job at this, but trying to show you slow flight. And so there might be a wind up here. I'm not sure what the winds are, and that could affect you a little bit. But slow flight is essentially trying to maintain your altitude and keeping that airspeed right above stall. So now let's turn back to west, and we'll try to get down to 3,000 feet. Let's get that bank angle back in. We're at 10 degrees bank. And you can see how fast it turns. So now we're on a heading of 270, which is west. And now we're within our limits again, finally. So we're at a little bit of power to start arresting that descent. And so this is good right here, 40 knots. We're at our altitude for the most part. And so that's slow flight. To recover from slow flight, we'll start by adding power. Make sure to keep the airplane coordinated with rudder. And then you'll slowly be pushing the nose down, because if you don't move the pitch, it's going to just climb because of the added power. And now we'll remove 1 notch of flap. And then another one. And another one. Everything's holding well. And then we just let the airplane accelerate, the nose comes down, because we need less angle of attack to keep the airplane flying level. And now we can reduce our RPM to a good cruise. A slower cruise, because we keep bringing it down to 0 basically for all the stalls. Alright, so now the next thing we'll demonstrate is a power off stall. This is also called an approach to landing stall, and in the PTS they're going to want you to demonstrate it as an approach to landing. So what we're going to do is we're going to set up for landing again. Bring that to 1500 to allow us to slow down. We're already below 110 knots, so we can do 10 degrees of flaps, and then the rest of the flaps can come down before 85 knots, which is here, so I'll go full flaps now. Once we pass through, well, we'll start descending now. Well, yeah, okay, so 60 knots, we'll pull power, and then we'll set up a descent, about 500 feet per minute. And now we're just going to slowly bring the pitch back to a point that it's just going to stall. It doesn't have to be anything aggressive. So the speed's dropping, we're still descending like we're landing, but now stall horn's coming on. And now right before the stall breaks, I'm going to show you how you want to keep the airplane wings level using the rudders more so than the ailerons. Because if you use the ailerons, remember when the aileron goes down on either side, it's going to create more drag, and all that's going to do is make directional control worse. So I'll try to show you the rudders here. Left rudder. Okay, holding the yoke back. And you can see I'm playing with the rudder pedals to keep the wings level. Now let's add a little power to make it really stall. Which it kind of already is, but make it a little bit worse. So if you start putting aileron, see, it doesn't do very much, except just make the situation worse. So let's recover from this. Full power. Bring the nose to level, take out the first notch of flaps. Yeah, we'll reset so we can do a little more controlled demonstration now. Instead of trying to hold it all the way, we'll get up to 2,000 feet. We'll just do a normal power off stall. Okay, let's add full flaps. We're below the wet arc. Okay, I'm at 1500 RPM. Okay, about 60 knots. Let's reduce throttle to idle. Set up a slight descent. And now we slowly bring the pitch back until it wants to stall. Keep bringing it back more and more. Okay, that's a full stall. Full power. Reduce the first notch of flaps. Stick forward. And now we climb at around VX. We have a positive rate of climb. We'll bring up the next notch of flaps. Everything's still good. We'll bring up the next notch of flaps. And now we're back at 2000. We'll level off and accelerate. So now we'll demonstrate a power on stall. Power on stall is also a departure stall. And so, just like the power off stall, we're going to simulate it more like real life. We're going to slow down to about this speed here. And then we're going to pitch up like we are for takeoff, add full power, and then we'll keep bringing the pitch back a little bit more to a pitch angle that we know is going to make the airplane stall. Again, so it doesn't have to be too violent. And in the procedure to recover, since we were at flaps up, it's a takeoff, departure stall, you just really have to push the yoke forward and maintain heading, and then climb back up. So add full power. And we'll put it to a position that we know the airplane will not like and it's going to stall. The wing will stall. We just hold this pitch angle. More right rudder. There we go. Push the nose down. And now we pitch for VX. And we recover. So power on can be pretty easy. The main things with the stalls is that you gotta push the yoke forward to break the stall. And then use your rudder when you're at much slower speeds to keep the wings level, and once you get your airspeed back, you can really use your ailerons again. So now the last stall we'll demonstrate is an accelerated stall. And so we're making sure we're going to be at or below maneuvering speed before we do that. Maneuvering speed in this plane is 100 knots roughly at max gross weight. That's what this marking up here is. But we're not at gross weight. And so maneuvering speed goes down when your weight goes down. So we'll slow down to about 70 knots here. Okay, so now we're going to get into, we'll add a little power now to maintain that speed. We'll get into a turn, and we're just going to try to stall it before its normal stalling speed. So we just pull back more and more until it stalls. There we go. Again, in real life it is fairly difficult to get the 172 to do an accelerated stall. You really do have to pull it through like that. Let's do one to the right. There's already a stall horn. Okay, right rudder, left rudder, left rudder. And so that's essentially an accelerated stall. And the accelerated stalls are important because when you're taking out your T6 or some other warbird from A2A and you're going through canyons and rivers and you pull a little too hard, you want to be comfortable with how to quickly recover when you're low to the ground like that. And so it's if it's a right turn like this, it's gonna stall over. You gotta get left rudder, right rudder. You gotta play with your controls and just practice with the accelerated stalls to make them work. And so the last thing we're going to cover now is spins. And a spin is when you have one wing stalled more so than the other. The airplane is stalled, but one starts getting stalled more than the other, and so that wing is going to drop more. And then when that wing drops more, it's going to start bringing the nose around like this, and then you'll see how that eventually develops into a stall. So let's do one to the left. So I've got full left rudder, full back stick. The procedure to recover from a spin is to reduce the power because you're going down, neutralize the controls, push the yoke forward, and opposite rudder to recover. and then you want to be very gentle with pulling back. And then once you're pitching up and you got enough you got good airspeed again, you apply your full power and climb up. And so one correction on the spin recovery is in the last two steps. You want to pull the power, neutralize the controls, and then you want to put full and opposite rudder, and then push the stick forward. That's the right order they want to hear you say in the check ride. And now essentially in a real spin you're going to do all of that almost at once. And also the PTS says that for all these maneuvers you won't do a spin on a check ride in the United States unless it's a makeup check ride for CFI. But all the maneuvers you have to do on your check ride, you have to accomplish above 1,500 feet. So let's do a spin real quick. Not a safe altitude for a spin, but I'll demonstrate one more. We'll do it to the right. Back stick, right rudder. And now power's off, neutralize the controls, full and opposite rudder, so left rudder, stick forward to break the stall. And now gently recover by pulling back. And that's the end of this video for slow flight, stalls, and spins. Leave any comments, feedback, and questions below, and I'll be happy to answer your questions. See you in the next video.